This video is on solving problems with infinitely sized tree diagrams. Um, so I came across this puzzle on a website called The Art of Problem Solving, AOPS. And in the puzzles section, there was this problem here. It was about someone called Winnie, and they were flipping a coin until they either get two heads in a row or three tails in a row. Whether they get either one, they must stop, and we want to find the probability that her final flip is heads. Now, this is a recursive probability question, and I found a really nice way to solve these types of problems. And I couldn't find many videos on it online. Well, many videos that went into it, into, just a bit more depth and give, you know, more examples or more varying examples. So I decided to make this instead. So the interesting thing about this question is she could just get heads in a row and then stop, or she could get tails then stop. But you also may get like heads tails heads, and then you could get another heads, in which case you would stop, or you might get another tails and then a heads and a tails, and it might just go on forever, and you actually might not get either one. It could just repeat forever as heads tails, even though it's very unlikely. You could just get heads, heads, then stop. You could get tails, heads, tails, then stop, because you've got three tails in a row. Or you just might have this infinitely repeating sequence, which just never gets anywhere. And I'll represent it as a tree diagram. So, we'll say that this is heads, and then this is tails. So then, after, say, you get heads, you might get another heads, in which case you would stop, and the tree diagram wouldn't carry on. Or you might get a tails. Okay, here you could get a heads or a tails down here. But say if you get two heads here, then you'd stop, and then the tree diagram would cut off there from that branch. Okay, you might get a tails here, and if you get a tails here, then you would carry on this tree diagram for heads, tails, and then either one would allow you to proceed, because that's not the stopping condition. But say if you get heads and then you get heads again, then you would stop. Or say if you get heads and then heads, you would carry on. You could get tails here. You would still carry on because you need three tails to stop. You could get heads, in which case you would still carry on. Or you might get tails, in which case you would stop because you've gotten three tails in a row. This could be heads and this could be a tails. You'd still carry on from either one because we still don't have two heads in a row or three tails in a row. If you get a tails here, you'd stop. If you get a heads, you'd carry on. If you get a heads here, you'd stop. If you get a tails, you'd carry on. I'm sure you get the idea, but these just carry on. Okay. This one here would stop because it's two heads. This one here would stop because it's two heads. This one here would stop because it's three tails. And yeah, you get the idea. So the way to solve these problems is to think about states. Now, you are obviously thinking, what are states? States are just positions in the scenario, in the game. Okay, let's just define some states. And it might seem a bit random or not very intuitive at the start, but I'm just going to ask that you go ahead with it, and then hopefully it will make a bit more sense as we do this first problem. Okay, so let's just say S, the variable S, represents just the starting state. So we've not got any heads yet or any tails yet. Okay, let's say the variable A represents us being currently on heads, and let's say the variable B represents us being currently on tails, and let's say C represents us currently being on tails. Okay, so these are all the possible states we could be in. We're not going to have a state for heads because that would just have that would just be a stopping condition. And we could have a state of being just currently on tails or being on tails. These ones you might think as B being encompassed by C, because you might think, oh well, we are currently on tails here, even though it's a tails. I would advise you to just separate them out and not try and encompass them. They shouldn't change your answer, but it'll just be a bit more difficult to actually lay out the problem. But if you can, you should lay it out in the most basic way ever. So, tails or tails, those are all the states. Okay? So these are what the states are. Okay, now what we need to do is we need to transition between states. Okay, so let's say we're at the starting state S. Okay, we need to somehow transition to A, right, to get in two A's, because then we'd have two heads, and that would be fine. Okay, so we need to transition between each state to get to HH. Okay, so that's what we're going to do with this. So let's say we start from S. Okay, from S we have a 1/2 probability of landing on heads. Okay, and we also have a 1/2 probability of landing on tails. So we have 1/2 probability of A plus 1/2 probability of B. Okay, so it's 1/2 probability of this or 1/2 probability of this. The or means that we need an addition. Okay, so we've defined state S now. S is completely fine. That's the only two options from S. You can't do anything else. Okay, how about A? Let's say we're currently on A. Where else can we go? Well, we could either have a 1/2 probability of getting another heads, okay, which would just which we'll call 1, and I'll explain why in a second. Or we have a 1/2 probability of getting a tails, which is just a B. Okay, I'll come back to this one here later. And then let's say we define B. Well, where can we get to from B? Well, if we're currently on tails, we have either a 1/2 probability of getting on heads, in which case we'd be at A again, so 1/2 probability of A, or a 1/2 probability of getting another tails, in which case we'd be on C, state C. Okay, now let's come to this one here. So the reason why I've put 1 here instead of, say, A, which you might have thought, because you might think, oh well, we're going to be on A again on, and so we should put A because that's going to be another heads. But the thing is, these transition probabilities, they define how to get from some variable, in this case here, from A to heads. Okay, and so whenever we get to our stopping condition, there will always be a stopping condition in recursive probability questions. Whenever we get to our stopping condition, if it's the one that we want, i.e. the heads, we would just put in a 1 there, because that would contribute to the total probability. Now, let's define C, and in this case, you're going to see that we're not going to use a 1, we're going to use a 0 in a bit. So from C, say we're on tails currently, we can either have a 1/2 probability of getting a heads, which would put us on A, or we could have a 1/2 probability of getting on tails, which would put us on B. But actually it wouldn't, because if we're on C and then we're getting another tails, that would give us a tails, which is our stopping condition. But it's not going to be 1/2 1, it's going to be 1/2 of 0, because this is not the stopping condition that we want. This would not contribute to the total probability of getting from any of the variables to heads. Okay, so these all describe how to get to the HH stopping condition. That's why we have a 0 for the tails, because that's not what we're getting to, that's not what these are describing. And that's why we have a 1 for the heads, because all of these define how to get from them to heads, not to tails. Okay, if we were defining them in terms of how to get to tails, we'd put a 1 here for the tails, and we'd put a 0 here for the heads. Okay, hopefully that makes sense. Okay, so here we've just got a system of equations. We can just solve these. This here is a 0. That gives, if you multiply by 2 on both sides, you get A equals 2C. Okay, and let's just put this into there. So we have B equals 1/2 of 2C plus 1/2 C. Okay, and if you just rearrange that, we get B equals 3 over 2C. And let's put 3 over 2C into there. So we'll have A equals 1/2 plus 1/2 of 3 over 2C, which gets us 3 over 2C equals 2A minus 1, or A equals 3/4 C plus 1/2. Okay, but now look at this. This one and this one, we can just solve these simultaneously, because they're 2 equations and only 2 variables. Okay, so let's just plug in, when A equals 2C, we'll plug in 2C into there. So we have 2C equals 3/4 C plus 1/2, which gets us C equals 2 over 5. And then we're going to plug this into here to get what A equals. So A is 2 times this, so A is going to be equal 4 over 5. And then we can plug this into here to get what B equals, which would be 6 over 10. And then finally we can plug in A and B into here to get what S equals, which will give us 7 over 10. And that is our answer. Okay, the reason why that's our answer is, well, let's just go back to the to when we defined the transition states. So the answer is 7 over 10, by the way. That's the final answer. That's the probability that our final flip is heads. It's because these these variables define how to get from the variables to the stopping condition. Okay, if say we solved for A, okay, this 4/5 represents what's the probability her final flip is heads if she already started on A, i.e. if she already started on a heads. This B represents the probability that her final flip is heads if she's already started on a tails. This 7/10 represents the probability that her final flip is heads getting there from S, i.e. S the starting state. So that's the one that we actually want, because that's the probability from the start of the game. Okay, hopefully that makes sense. So let's look at this, for example. Let's try and understand this intuitively. Remember, A was the probability that we are on heads. Imagine if we solved for A, okay, we'd expect the probability for A to be very high, because getting from A to HH, which is what this is defined by, that should be very high, because we only realistically need one more, because it's 1/2 of 1. Okay, compared to the tails, so we'd expect C to be very low probability, whereas A would be very high, which is what we see here. Okay, because this 4/5 represents how to get from A to heads. This C represents how to get from C, which was tails, to heads, which is much lower, as you can see, because you only need you need 2 more in a row to actually get heads at minimum. Okay, hopefully that makes sense. So this represents how to get from the starting position to heads. This represents how to get from A, i.e. just heads, from currently being on heads to heads. This represents how to get from being I think this one was tails to heads, and then this one was how to get from tails to heads. Okay, hopefully that makes sense. So our final answer is 7/10, because that's the probability from the start of the game, which is obviously what we're looking for. Let's look at this other question. So a player rolls a fair 6-sided die. If he gets a 5, he stops. If he gets any other odd number, he rolls again. If he gets a 6, he stops. If he gets any other even number, he rolls again. Find the probability of his last roll being a 6. Okay, maybe just pause to understand the question there. But we're going to answer this question in terms of states. Now, the reason is because this is going to be a recursive probabilities question, because, it could just go on forever. He might just get tons and tons and tons of even numbers or odd numbers, and he's just going to keep on rolling again forever and ever. And he might just never even get a 6 or even a 5. Okay, now some of you may see this question and instantly know the answer, just because of the symmetry of the question. If you can see that, then you'll already know what the answer is. If you can't, I'll show you it later on and you'll understand why that is the answer. So S is the starting state. Okay, let's just say S is the starting state. This is basically the same thing. You always want to have a starting state. Okay, and then you want to have a next state. Well, what are the possible states? Okay, so we can either be at the starting state, in which case we've not rolled at all, and okay, what's the next state? We could land on an even number. So our next state could be it could be currently being on an even number, and not including 6, because that would be the stopping condition. Another state could be us just currently being on an odd number, excluding 5, because 5 is the stopping condition. Another state could be landing on a 5, which is one of the stopping conditions. And another state could be landing on a 6, which is just another stopping condition. Okay, we don't need any even number followed by another even number, because that's not how the stopping condition is based. It's just this. Okay, hopefully that makes sense. I'll just put these to one side and let's actually define them. So from the starting state, let's see where can we actually move to from the starting state. So landing on an even number that's not 6. Okay, well, there's 2, 4, 6. So there's 3 even numbers from 1 to 6. Okay, and we can only land on 2 of them. So 2 of the 6. We don't want to be on 6 because that would be a stopping condition. So there's a 2/6 probability of landing on A. So 2/6 times by A. Or we could land on an odd, which has probability 2/6, because there's 3 odd numbers. There's 1, 3, 1, 3, 5, between 1 and 6 inclusive, and we don't want 5 because that's the stopping condition. That would be C. So that's only 2 out of the 6, not 3 out of the 6. So that's 2 over 6 B. Or there's a 1/6 probability that we actually land on a 5, in which case that would be 1/6 times by 0, because this does not contribute to the probability we want. We're looking for the probability that the last roll is 6, so this would be a 0, because that's not the stopping condition that we want. And then finally there's a 1/6 probability of landing on a 6, in which case we'd stop, so 1/6 times by 1. I won't spend too much time defining the probabilities now, because I hope by now you get the main idea. So again, from A we have oh wait, actually no, this one, I will say something about this one. Think about A. Imagine we've landed currently on an even number. Where can we go next? Well, we could go to 26A plus 26B plus 160 plus 16 times 1. But that's just the same thing as S, right? Because these are completely independent of each other. It's not going to affect the next one. So from A, we could just get to S. That's the only place we can go. Okay? And then you might say, oh, and you can also have 1/6 times 0 plus 1/6 times 1, but no, you don't need to include that, because that's encompassed. That is S. S already includes that. Okay, you could just write this out in full and then realize, oh wait, that's S. You just put, and then you just write S instead of this full thing. From B, similarly, you could just get to S. That's the only place. From C, you just have 1/6. It'd just be 0. It'd just be 1/6 0. If you're on C, it contributes 0, so that's just 0. And then D would be 1 because it contributes 1. Probability of 1. Okay. You just replace all the A's with S's, all the B's with S's, and the D with 1. There is no D. That would be this one, which is already 1. You'll get this, and then you rearrange, and you'll get S is a half. S is a half. Some of you might have seen this. Look at the symmetry of the problem. It's basically the exact same on either side, right? So it doesn't actually matter which stopping condition we get, because it's both they're both the same. You know, getting a number or rolling again, or getting a different number or rolling again, you know, it's, if you notice the symmetry, you'd say, oh well, it's the exact same thing on both sides, so that's just a probability half. I'm standing on a number line from 0 to 10 inclusive. We are only whole numbers. Okay, I start on the number 1, and I have a 1/3 probability of moving down by 1, and a 2/3 probability of moving up by 1. The game stops if I reach either 10 or 0. If I reach 10, I win, but if I reach 0, I lose. What is the probability that I win? Okay, now this question is kind of like the first question about Winnie, but just much more difficult. But using states can actually help us to really break it down and help us to understand it. This question, you can answer it really quickly using recursion. Just if you think about the term recursive probabilities, use this idea of recursion. And if you do computer science, you'll know about recursion. It helps you solve this problem really quickly. But I'm not going to go into those high level ideas just yet, or even at all this video. I'm just going to stick with recursive probabilities, okay? So this is technically recursion, but you know, the other way is a bit more quicker, it's a bit more compact. Okay, so let's just have a starting state. S equals the starting state. Let's say A is position 2. Okay, S, the starting state, would just be position 1. B would be position 2, C position 3, etc. all the way to H, which would be position 9. Okay, this is fine. I'm sure this this makes sense. Okay. Okay, let's how do we define S? Well, where can we get to from S? Well, we have a 1/3 probability of moving down to 0, in which case that would contribute 0, because that would be the stopping condition that we do not want. So it's either 1/3 chance of 0 or a 2/3 chance of increasing by 1 to get into position 2. Well, position 2 is A, so we'll do that. Now from A, where can we get? Well, we could go down by 1, but if we're going down by 1, we're going from position 2 to position 1. Position 1 is just S, so that's 1/3 times S, or 2/3 times by moving up by 1, which would get us to position oh, that was messed up there. Does that also say position 2 there? This should say position 3, 4, 5. So this would be 1, 2, 3, 4, 5. H being 9 is still correct, though, but this B here should be a 3, and this should be a 4. So B should say 3, C should say 4. Sorry about that. Let's go back. So we have 1/3 chance from A of moving down by 1 to get back to S, or moving up by 1 to get to B. I think I've already said that. And then from B, we could get, currently we're on position 3, B is position 3. We could move down by 1 to get to position 2, which would just be A. So that would be a 1/3 probability of getting to A, or a 2/3 probability of moving up by 1 to get to the next position, which would be position 4, which is C. And then from C, you'd move back by 1 to get to B, or move forwards by 1 to get to D, with probabilities 1/3 and 2/3 respectively, and you'd carry on, okay? I'm sure this here makes perfect sense. And then at the end, when you're at H, you could either move down by 1 to get to position 8, which would be what is that? That would get us G. Obviously, it's right here. So you could move down by 1 with probability 1/3 to get to G, or you could move up by 1 with probabilities 2/3 to get to position 10, which is just a 1, because that's the stopping condition we want. Okay, so we just need to solve this very simple system of 9 equations. It's not very simple at all, but actually, you know what? It's actually not too bad. Okay, let's just go through it. So here we've got H equals 1/3 G plus 2/3. Okay, this is a good place to start. Let's just rearrange, and if you do, you'll get G equals 3H minus 2. Okay, so we'll plug this G equals 3H minus 2 into here. So you have 3H minus 2 equals 1/3 F plus 2/3 H. Okay, but oh yeah, that's fine. So that means we can write F in terms of H. If you just bring the 2/3 to the other side, you'll get this times by 3, and you'll get F is 7H minus 6. Okay, the next one would be F equals 1/3 E plus 2/3 G. We know that F is 7H minus 6, and we know that G is 3H minus 2, so we'll plug those two into there. And then you'll rearrange for E, and you'll get 15H minus 14. And basically, we're just going to be carrying this idea down. We're just going to try and write every single one in terms of H. Okay, so, I'm not going to go through all of them, but hopefully you can see we're just taking like the two previous ones and we're plugging it into the one next. And then we're just writing that one in terms of H's. Okay, and if you go down, you'll get this. And here you might notice the where you could use recursion. If you notice, all of these are one less than the variable part. Okay, which is pretty interesting, I think. Anyways, so you'd get all this. So we have S equals 511H minus 510, and we've got A equals 255H minus 254. Now we've gotten these, let's look at this last one here, okay? Because every other one except for the last one and beginning one have 3 variables, except for this one, which has 2 and 2. Okay, so those are the ones where we're actually going to get our first solutions from. So let's plug in S equals 511H minus 510. Okay, and we'll plug in A equals 255H minus 254 into there. If you do, you'd rearrange and you'd get H is 1022 over 1023. However, that is not the answer. Be careful. The variables that we're calculating the probabilities for, that represents how to get from that variable to the desired stopping condition, i.e. 10. So this is saying if we started on H, i.e. if we started at position 9, the probability that we win, i.e. get to position 10, would be 1022 over 1023, which is very, very close. It's like 99.9%. Okay, but we're looking for S, because that represents how to get from the starting state, from the beginning of the game, to position 10, which is obviously the case here. We're not going to start at position 9, because we start at position 1, which is S. Okay, so we'll plug this H into here, okay, to get what S equals. And if you do that, you'll get 512 over 1023. You don't even need to work out the rest of these, but that tells us that to get from position 1 to position 10, with all this recursion, that is probability 512 over 1023, which is about 50.5%, I think. I'm not too sure, you can check that yourself. But that is the final answer. Okay, I've gone ahead and written all of the other probabilities, so I got an online calculator to do it for me. Just so I could show you this is the answer. But let's just look at this. This is the last thing I'll say, and then that'll be it. Okay, I know this video is gotten pretty long. It's maybe just under half an hour, I think. But But the last thing I'll say is, just look at this. So this is position 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sorry, not 10. This is position 9. That's 1, 2, 3, 4, 5, 6, 7, 8, 9. Can I just not count? I might be just tweaking out. But just if you look at all this, oh, it's because this one B is repeated. So it'd be 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep. Now look at this. As we get closer to the number 10, to the number 9, sorry, the probability increases, which is what we'd expect. Because imagine we started on position 9. The probability to get to position 10 would be super high, right? Because we're right next to it. But say if we go from position 1, that probability is so much lower. And you can see that as we get further and further away from position 9, or position 10, sorry, the probability decreases, which is what we expect. Okay. So yeah, that's pretty interesting. Hopefully you can take this idea of using states to a lot of recursive probability questions. I think it might work for even every single one. Just experiment, try it out, see how it is. But that's the end of the video. Thank you for watching.